So again, the question is, if I hold or press a book against a wall, do I need to press up in order to keep it from falling? And you said no. So, Joseph, what are the forces acting on that? Let's do this. Let's say that's the wall, okay? What are the forces acting on it? Get the obvious one. Which way? Was it accelerating down? Was it accelerating up? So I know there has to be an arrow the same size pointing up. What force is that? Is it? Let's pause for a second. What else? Well, I was applying a force with the meter stick. I was pushing this way. We have F applied. Is it sinking into the wall like quicksand? Is it flying off of the wall like Superman? So there's a force the same size in this direction. What force is that? That's the normal force. You can think of a wall as a floor just tilted sideways, and in the same way that the normal force goes 90 degrees up from a surface that's level, it's also going to go 90 degrees out from a wall that's vertical. Does that help you figure out what force must be pointing up? The tug of war is right here, so friction needs to be the same size as what? Otherwise, it's going to slide down. How can I make friction bigger? Friction is what times what? How can I make the normal force bigger? Push harder. Because as hard as I push, that's how big the normal force will be, Neha. That will make friction bigger. I could also change mu. I think if my wall was made out of sandpaper, I would not need to press as hard as I was having to press there. But you can actually feel it. In fact, you may have taken this for granted, but I'm willing to bet all of you have carried something like a book like this with your hand above it. What you're really doing is, think about it, you're squeezing inwards to resist gravity. What are you doing? You're creating two small applied forces, one from either side, which gives you two normal forces pointing out, which gives you enough friction to resist gravity. What happens if I relax my fingers? In fact, I can feel, you can't tell right now, but I'm feeling through my hand, it's just about to start to, there. I could feel that the contact force was getting weaker and weaker. I could just feel through my fingers, it's almost ready to fall. You kind of do that whenever you carry something. You take it for granted, but there's some really neat physics going on there, I'd like to say. That's nothing to do with today's lesson. Let's start today's lesson. What was the title of today's lesson, Jake? Lesson 7. What if there's more than one mast attached with ropes? The good news is I've kind of snuck in how to do it already. You just didn't realize that I'd snuck in how to do it already. So in these problems, we have several objects. We'll start out with 2, connected by strings. And the easy approach is to pretend that we can treat this system as a single mast. In other words, everyone look up for a second. Sorry for those of you at YouTube. Here is my 2-mast system. Here's my argument. If the ball in my right hand on your left is accelerating at 3 meters per second squared, this one has to be accelerating up at 3 meters per second squared. Because they're attached on the same string, their acceleration is going to be the same. We are not going to let you do this. Everyone look up. You're not allowed to do that. Okay? That has a name in physics. Believe it or not, the proper name for that is a jerk. It's a physics term. We're not going to deal with jerks in this classroom, which has, I guess, a double meaning. But what I mean is we're not going to let you yank on the rope and have one object accelerate differently. It's going to be a smooth pull. But can you see they are accelerating at the same rate as long as I do that? Is that okay? Because of that, what we're going to do is we're going to pretend we're just dealing with one big ubermass. Let me show you what I mean. I like example 1. No, I don't. Example 1 is too easy because there's no friction. But we'll start with this. It says find A, the acceleration, and B, the string tension. Well, any thoughts on what this might be a good job for, Jet? Okay. Is there more than one mass? Say yes. Okay, I generally start on the left and work my way right. You don't have to, but if you want your free body diagram to look like mine, start on the left and work your way right. What are the forces on the 3 kilogram mass, Jet? Get the obvious one. Is there more than one mass in this question? Say yes. Instead of mg, I'm going to call this m1g. I'm going to call it mass number 1. Are we sinking into the ground? What else pointing up? Bigger, smaller, or the same size as M1G. And because it's M1, I'm going to call this normal force number 1 to go with mass number, wait for it, 1. What else? Is there a rope touching this mass? Then there's tension. It's feeling a force to the right. Tension. Is there friction in this question? Is there friction in this question? Okay. If there was, I would have one more force pointing that way. We'll do one in a little bit. It makes the question longer, but not really harder. Those are the 3 forces acting on mass 1. Mass 1 isn't sinking into the ground or flying into the air. It's accelerating to the right, not because of the 20. It doesn't feel the 20. It feels the tug of this rope here. Tension. What are the forces acting on mass 2? Get the obvious one. Is there more than one mass? I'm going to call this M2G. I'm going to be fussy. If you haven't numbered your masses and you ask me a question, I won't help you because I don't know which M is which. I can't follow you. So just number your masses. And what else, Jet? And I'll call it normal force number 2 to go with mass number 2. We have this 20 coming from off the page. What's the name that we've given to the mystery force coming from off the page? Okay, so we have an F applied. We're missing one more. Yeah, tension is pulling this way. This is a Newton's third law of forces come in pairs in the middle there, but I'm telling you, tension is slowing the 2 kilogram mass down. It's speeding the 3 kilogram mass up. Okay? Which way is this accelerating? It has to be accelerating to the right because we're on a frictionless surface on ice. Even a tiny force will cause it to accelerate to the right. So who's winning? To the right. Now, what we're going to do is we're going to walk along the rope. We're going to write an equation for that right there, along the rope. Who's winning? F applied. What I'm really saying is anything to the right is going to be winner plus. Anything to the left is going to be loser minus. Loser minus, right? So you ready? I'm going to scroll down. You've got the free body diagram still. Jet, who's winning? More specific in your free body diagram? And now walk along the string. You run into a tension, a T. See it? Which way is it pointing? To the loser, not the force, not, or maybe you, no, the force, not you. Keep walking, keep walking. You run into another tension. Which way is it pointing? Winner plus. Okay? What about M1G? What about M2G? Are they along the rope? We're writing an equation along the rope. Is there any other forces along the rope? Equals. Here's the only tweak. Do we have more than one mass? Do I have forces from more than one mass? Yeah? Then I have to have more than one mass on the right. On the right, it's going to be M1 plus M2 times A. I'm lazy. You all wrote that, and that's fine. What I usually just write is this. M all A. Because that's M1 plus M2. Or if there's 3 masses, that's M1 plus M2 plus M3. You can leave it as M1 plus M2. On the next question, we'll go M all A. By the way, that's actually what we've been doing all along, because when it was 1 mass, that's technically M all A2. That's why I said you've kind of been sneakily doing this. Jet, put your pencil down, stretch. Ah, do you know why we're stretching? Oh, we're losing tension. That's why. I love losing tension. It's so relaxing. It's always good to lose a little tension, isn't it? What happens to the T's? What's a minus T plus a T? We're losing tension, so stretch it out, baby. Losing tension, right? What did they want me to find in part A? How will I get the A by itself? Trevor's theorem, but I'll divide by M1 plus M2, by M all. I'll get this. A equals F applied divided by M1 plus M2. You know what, Jet? This might be so easy that you can do it in your head. What's F applied? What's M1? M2? 20 divided by 5. I bet you can do that in your head. Units? I'm glad you caught yourself because I was going to come over the top rope at you there. And yeah, I'll go to 2 sig figs to show off meters per second squared. So the only difference, if you give me more than one mass attached by a string, I'll write an equation for all of them and find the acceleration of all of them. Okay? Oh, Jet, what did B want me to find? Why can't I use this equation to find tension? I could find it if there was 2 T's. I don't think I have 2 T's. I have no T's. I have no tension. You know why I can't use this equation? Are you ready for my best, worst joke ever? I have a tension deficit disorder. Huh? Huh? I have a deficit of tensions. Nothing. Okay, fine. So our strategy is going to be write an equation for everything to find the acceleration of everything. And then, you know what our strategy is going to be to find an individual force? Write an equation for an individual mass. Did you hear me use everything and individual in 2 different contexts there? In other words, to find tension, let's write an equation for this mass. Jet, let's quickly redo the free body diagram. We had M1G, normal force 1, tension. I don't care about mass 2 because I'm looking for an individual force. So I'm going to write an equation for an individual mass. Which way is that 3 kilogram mass accelerating? Which way is the winning direction? Same answer. Look at my free body diagram. Who's winning? Yep. Who's losing? It's a trick question. Nothing. I get this. Tension equals what? I'm just looking at one mass, M1A. I'm not looking at M all. You know what? This is so easy, I bet you can still do it in your head. What's M1? What's A? What's tension? Units. It's a force. There you go. You want me to find the acceleration of everything? I'll write an equation for everything. Oh, you want me to find an individual force? I'll write an equation for the individual mass. Now, Shane is stretching it out right now, losing tension. I like that. But Shane, you might be saying, yeah, Mr. Do It, but what if I had done the other mass? You know what would be really cool? It would be really cool if it didn't matter which mass I picked. I would get the same tension no matter what. That would be pretty cool. So let's check the other mass. The free body diagram there, let's quickly redraw it. Shane, you and I, it was M2G. It was normal force 2. We had F applied. And we had tension. Ignore the 3 kilogram mass right now because we're doing an individual force, so we're just going to look at an individual mass. Which way is the 2 kilogram mass accelerating, Shane? To the? Who's winning? Who's losing? And that's going to equal M2A because that's what I'm writing an equation for. I'd like to get the T by itself. What's right in front of the T that I don't like? Ugh. Swappy dance. I'm going to plus the T to that side. I'm going to minus the M2A over. F applied drops down like a domino. Minus the M2A. And if you don't mind, I'm going to put the T equals over here on the left because that's where we're used to seeing the thing by itself. T is going to be, what's F applied as a number exactly, Shane? Minus, what's M2? What's A? We figured it out. Yep. You know what would be really cool? It would be really cool if, really using your calculator, Ethan, it would be really cool if that also worked out to 12. Well, what's 2 times 4 in your head, Shane, without a calculator, Ethan? What's 20 take away 8? So it doesn't matter which mass I pick. I'll get the same answer no matter what. One of them was a little bit easier. I probably would have chosen this one because it was easier to get the T by itself. But it doesn't matter. I'll usually pick the equation that's the cleanest, that's got the least junk on it. Why would you have a whole bunch of... Wait, I haven't got to yuckier ones, but there'll be some where you'll say, obviously, yeah, I want to find tension from that one, not from that one. But it doesn't matter. Is that okay? So what's our strategy? If you give me more than one mass, it's winner minus loser equals M all. A. And then you want me to find an individual force? Fine, I'll write a free body diagram for an individual mass, write an equation for an individual mass, and I'll use the A that I just found of everything. That's also the A of the individual mass. Another one we like to do is if we have a mass hanging over a cliff. First of all, if we look at this picture, which way must these guys accelerate if there's no other external forces? I think right and down. There's no way on its own that this is going to spontaneously start crawling this way, lifting this up. We have an unbalanced force. In fact, what's causing this whole chain reaction is gravity acting on the 2.5. So example C3 says, find the acceleration, find the core tension. Preston, you know what this is a good job for? Good yawn. I'm going to start with the 6 because it's on the left. What are the forces acting on it? Get the obvious one. Which way? Is there more than one mass? I'm going to call it M1G. What else? Which way? Same size, bigger, or smaller? Since it goes with mass 1, I'll call it normal force number 1. What else? Is there a rope? So, you're feeling a little right now? Yep. Is there friction? I think the wheels are meant to indicate ignore friction. It's just going to roll. Those are the forces acting on that particular mass. What are the forces acting on M2? Get the obvious one. What else? Is M2 sitting on a surface? So is there a normal force? No, that's a common mistake. Kids get kind of normal force loopy and start sticking it everywhere. Only if you're sitting on a surface, or if it's vertical, if you're pushing against the surface. Okay? Which way is this thing going to accelerate? Yeah, I agree. So here's my question. What's winning? Anything that once it gets to here is pointing which way? Starts letter D, down. Who's winning? Sorry, say it again. Which force? Which one? There's two of them in this question. Can you say something and then a number and then G? Yes! That's what's causing this whole chain reaction. I'm sorry to be that fussy, but you can see we kind of have to be. If you say gravity, I got more than one. Okay, what's causing this all to start to accelerate is there's an unbalanced M2G pulling on the 2.5. Now, we've just defined once it gets to here and is pointing down as positive, winner. What about this tension? Winner or loser? Now, this tension, if you follow it, when it gets to here, which way will it be pointing? This tension, when it gets to here, will be pointing up. Okay? You understand what I'm getting at, okay? Got to use your Sesame Street imagination a little bit, but I'm going to argue that when it comes around the corner, it's going to be pointing which way? Did you side down on the right over here was a winner or loser? What about this M1G? No, we're writing an equation along the rope. Is M1G along the rope? M2G is, not M1G. We're done. What's that going to equal? M all A. How do I know it's M all? Well, I have forces from more than one mass on the left. I better have more than one mass on the right. Put your pencils down. Come on, join me. Stretch it out. Come on, you know you want. Wow. Why can we stretch? Yeah, we're losing tension. Losing tension's relaxing, right? You need to relax, lose some tension. Yes? Okay. Mr. Dewick, are you going to do that on every one of these questions? No, I would never. Maybe. What are we trying to find in part A? Get the A by itself? Trevor's theorem, except we're going to be dividing by both masses with a plus sign in between them. Okay? So on the next line, I think the M2G would just drop down like a domino, and I'll have M1 plus M2, M all. All right. What's M2 as a number, Presley? G? G? Good. And then M1, 6 plus 2.5. All of you want to practice typing this into your calculator. I have a bit of a built-in error check. If I cut the rope right there, what's the fastest the 2.5 could possibly accelerate? And it's being slowed down by the inertia of the 6. You're going to get an answer less than 9.8. So practice typing this in. I know on my calculator I can get away without brackets on the top, but I definitely have to have brackets on the bottom. Should get 2.88. Okay? What does part B want me to find, Presley? Why can't I use this equation here to find tension? T's cancel. So, well, pick a mass. We're going to write an equation for an individual mass. I can either use the 6 or the 2.5. So here's what I heard. 6.5. So you know what? Just this once, we'll do both. Okay? On the left-hand side, you'll use the 6, which is what you suggested. So let's write an equation. Which way is this 6 kilogram mass accelerating to the? Who's winning? Who's losing? Trick question. So here, I would go tension, no loser, equals M1A. If I use Julian's suggestion, which is valid, who's winning, Julian, in this one, in the 2.5? M2G minus who's losing in the 2.5? And that's going to equal M2A. Just writing an equation for that mass. Which of those is slightly easier to get the T by itself? I would have gone with the 6, but you can see both of them, meh, they're not that tough. So this half of the class, do the swappy dance. When you do that, I think you'll get tension equals M2G minus M2A. M2 is 2.5 times 9.8 minus 2.5 times answer button. The left half of the class, you folks, I think you'll be able to just go 6 times, I'm going to write 2.88, use your answer button. Those of you on the right half of the class, you're going to go 2.5 times 9.8 minus 2.5 times, again, I'll write 2.88, but you use your answer button. So you folks have gone 6 times 2.8 times answer button. If I go 2.5 times 9.8 minus 2.5 times answer button, almost missed the 9.8, Mr. Dewick. I think that's what all of us got, 17.2941175, yes? So I would have gone with Presley's way, although your way, honestly, I can do the swappy dance in my head and go straight to the numbers and get there too. It's really whatever. No matter what, tension equals 17 point what newtons? 3. Yep. Quick, money. Let's kick it up a notch. Let's bring in some friction. I like example 4. I like example 4. Example 4 is a nice question. It's very similar to the one we just did, but I guess this 3.2 is going to be sliding across the table. Again, there's no way that on its own it can start going that way. So if we are accelerating, we're accelerating down and right. It's possible friction could be so big that nothing's moving, but let's assume something is accelerating. It says find the acceleration, find the chord tension. Okay, Andrew, how am I going to start? Yeah, thank you. What are the forces acting on 3.2? Get the obvious one. Is there more than one mass? I'm going to call it M1G. Keep going. I'm going to call it normal force number 1. Keep going. I see a rope. Keep going. Do they want me to include friction this time? Which way do you think the 3.2 is going to slide? So which way is friction going to point? And I'm going to call it friction force number 1 to go with mass number. Wait for it. 1. Okay. Easy notation, takes 1 second to keep everything organized. Those are the forces acting on mass 1. Mass 2, what are the forces acting on it? Get the obvious one. What else? What else? Have some confidence. Tell me. Good. Yeah, nothing else. No normal force. We're not on the surface. I don't see anything else. And again, we're going to now write an equation along the rope. Okay? So, what's the first thing they want me to find? Who's winning? I totally disagree. Tension is not. And that's not going to help us find the acceleration because sorry? Which one? There's several of them. What's causing everything to move, to accelerate in the first place, Andrew, is that unbalanced gravity right there. So anything that ends up pointing down once it gets to the right over here is going to be winner plus. Anything that ends up pointing up once it gets to the right is going to be loser minus. So let's write our equation. I agree. M2G, and now walk along the rope. This tension here, winner or loser? Winner, loser minus. What about this second tension? Follow it, follow it, follow it, follow it. When I get to here, I think it ends up pointing down in the winner plus, yes? Ooh, friction. Again, if you follow it, follow it, follow it, follow it, follow it, I think when it gets to here, I think it ends up pointing loser up, does it not? Because the arrow is kind of bent around the corner. So friction is a loser. Are there any other forces along the rope? The most common mistake, kids want to include gravity. No, it's not along, they want to include M1G. It's not along the rope. If it needs to be there, it'll show up. Equals what? Good. How's your day going, Andrew? Put your pencil down and lose a little tension. Come on, join me. Oh, these are such relaxing questions. Why am I stretching? Oh, love it when you lose tension. Beauty. It's like a little spa treatment, every one of these questions. What are we trying to find in part A? How? So, you know what? I'm going to use Trevor's theorem. Look up, everyone. I am good if on this line you go yoink. M all is M1 plus M2. Okay. A is going to be M2G minus, I don't know, friction. Oh, wait a minute. Friction is what times what? So look up. Let's write down mu Fn1. I don't know Fn1. Oh, but look. Another force the same size as Fn1. Which one? So I wrote that down. I'm going to cross it out, and next to it, I'm just going to say, it's that. Is there anything else on the top I haven't written yet? All over M1 plus M2. Let's stick in numbers. M2, 2.8. G, 9.8. Minus, what's mu? I don't know what's mu with you. 0.12. M1 was at 3.2. Times 9.8. 2.8 plus 3.2. Or 3.2 plus 2.8. When you're adding, it doesn't matter. This is the level of difficulty typing-wise on your calculator that you want to become comfortable with. I think I'm going to have to put brackets around the top and brackets around the bottom. I got, you get 3.94613, I guess 3.95 if I round off properly. Units, Andrew, it's an acceleration. Good. Good. What's part B you want me to find? Which mass looks cleaner to find tension with? I would use M2. I won't take marks off. Go ahead and use M1. Totally doable. Get same answer. I would use M2. There's way fewer forces. It's not as cluttered. This is what I meant earlier when I said you'll usually be able to tell which is the cleverer one to go with. What's my equation? Which way is M2 accelerating? Who's winning? Who's the loser? What's that going to equal? Not M all, just M2, because now we're writing an equation for a single mass. Yep. How will I get the T by itself? Ah! Lovely. Plus the T there, minus the M2A there. And I'll get the M2G just dropping down like a domino, minus the M2A. And then, Andrew, do you mind, instead of writing equals T, I'm going to put T equals on this side, because that's where we're used to seeing the thing by itself. M2, I forget. 2.8. G, 9.8. Minus M2, 2.8. A, I'm going to write 3.95, but you know I'm using my answer button. If you had used mass 1, by the way, you would go tension minus friction equals M1A. You would end up going M1, 3.2, times A, plus friction, which is mu, times the normal force. I don't know the normal force. Oh, but look. Those that did the swappy dance method, did you also get 16.39082 and change? Yep. So no matter which one you pick, it works. But using this one, using the, hello, Mr. Newick, there we go. Using this one, it's way uglier. What was it, 16.4? Units, Andrew. Yep. Example 5. I think this is what I'm finishing with. Yeah, this is what I finish with. We can even handle more than 2 masses. In fact, we can handle as many as we want. I'm going to give you a couple of 3-mass questions in your homework. I won't give you a 3-mass question on your test, maybe as a bonus, but not as an actual question, because Honestly, I could give you a 10 mass question. It would just take such a stinking long time. I don't want to go there. All right. I feel pretty limbered up. Danielle, are you ready to go? It wants us to find the acceleration and the what? Ooh, that means there's more than one tension because there's more than one rope. I'll probably call one rope tension 1, and I'll probably call the other rope tension, okay? Or some people use tension L for left-hand side and tension R for right-hand side. I don't care. I think numbers because I'm a math nerd. How are we going to start out? What does that mean? How are we going to start out? I think the line you're looking for is this is a job for a free body diagram. Let's try that again. Scene 1, act 1, take 2, and action. Cut. Yeah, here we go. It's a free body diagram. Good. What are the forces acting on the 1 kilogram mass? Because more than one mass? I agree. Is there more than one rope? Tension number 1. What are the forces acting on the 9 kilogram mass? Good. Slow down, girl. Normal force number 2. You said tension 2. I guess that's this rope you're saying to the right. What would this rope be? Tension number 1. Because forces come in pairs. There's the pair. Okay. And I heard somebody else say a force. Which way? Well, we need to figure out which way that 9 kilogram mass is going to accelerate. Daniela, how big is this mass? How big is this mass? Is this going to be accelerating to the right or to the left? Because the 8 kilogram mass is bigger. So if it's sliding to the right, which way am I going to point friction? And I'll call it friction force 2 to go with mass number 2. Do you see why I called this one? I forgot to put the 2 there. Tension 2, this is the second rope. The first rope, let's call all the tensions tension 1 because they'll be the same. Ooh, what are the forces acting on the 8? Get the obvious one. What else? Which one? Yep. Is it sitting on a surface? No normal force. We already decided this. Which force is the winning force? M3 is not a force. What? M3G. So this thing is accelerating like that. What I'm really saying is anything, once it gets to the bottom right corner, if it's pointing down, winner plus. If it's pointing up, loser minus. That was kind of fun. So, M3, and again, going to walk along the rope. That's our routine. So it's going to be M3G, tension 2 here, winner or loser. Yep, keep going. What? Yep. Keep going. Yeah, because if I follow it, it does end up pointing up when it bends around the corner there. Ooh, what about friction? If I follow it, I think it also ends up pointing up. So it's loser minus. Keep going. Now you might be tempted to say because it's pointing up, it's a loser like this one. But if you follow it, I think it ends up pointing down on this side, does it not? So, winner plus. This M1G, again, you might be tempted to say, well, it's pointing down like M3G, it's a winner plus. But again, follow it with your eyes, I think when it gets over to here, I think it's pointing up, is it not? It's a loser minus, that M13. That's all the forces along the rope. That's going to be M all A. Everybody, put your pencils down. Got a double spot treatment. Oh, stretch it out, folks. Come on, you know you want to. Why am I so relaxed? Twice. We lose these two. That's already relaxing to lose a little bit of tension, but losing even more tension. Yeah. M13 instead of M1G. That's a little confusing, isn't it? And I didn't put a G there? After I told you to put one there? Terrible. What are we trying to find? Trevor's theorem. It's going to be divided by M1 plus M2 plus M3. That's what M all means in this case. Because I've got forces from all of those on the left. I better have that mass, all of them, on the right. So it's going to look like this. A equals jump M1 plus M2 plus M3. We'll have M3G dropping down. We'll have, what can I write instead of friction force number 2? Friction is what times what? So it's going to be mu times normal force number 2. And then minus M1. Although, what could I write instead of normal force number 2? Because I don't know normal force number 2. Oh, but look. Another force the same size as normal force number 2. See the little chain of reaction of events we put together there? A is going to be, what's M3? G, 9.8. Minus, what's mu? I don't know, what's mu with you? What's mu? 0.25? What's M2? Yeah? G minus M1, 1 times 9.8, all divided by 1 plus 9 plus 8. That there is about as tough as I'm going to be asking you to type this year. So try typing this one. If you can handle this, you're in pretty good shape. Because that's 3 things on the top, brackets around the top, and 3 things on the bottom, brackets around the bottom. Did you get 2.586 and then the ones repeat? 2.59 is what I'll write. Meters per second squared. Great job. Okay. Are we done? No. What else did they want me to find? I don't think they wanted me to find tension. I think they said tensions, plural. Yeah? Okay. You know what? Which mass would I not want to use at all? Look at your free body diagram. Which mass kind of is screaming, yeah, run away from me? M1, M2, or M3? Yeah. So let's write an equation for M1. First of all, which way is M1 accelerating? Which way is the winning direction for M1? Same answer. Look at M1 on your free body diagram. On M1 only, who's winning? Which one? There's 2 of them. Okay. On M1 only, who's losing? What's that going to equal? M1A. On the right-hand mass, the 8, I think it was. Which way is the 8 accelerating? Who's winning? Who's losing? What's that going to equal? M3A. Bit of a problem. We're going to be using A twice, so my answer button trick won't work. Probably what I would do is I would jot down somewhere that A is 2.586 and a bunch of ones. I would probably just in the margin, A is 2.586 and the 1 repeats. I'll use my answer button for the first one, and I'll just put a bunch of ones in for the second one. How will I get the T by itself over here? Minus or plus M1G? How will I move the M1G over? Yeah, plus it. So, what was M1? 1 times answer button plus 1 times 9.8. I know multiplying both of those by 1 makes no difference. I could have gotten away with not typing the ones, but I just wanted to let you see how it all fits together. Yes? And I get the left-hand tension is 12.4 newtons. How will I get the T by itself on the right-hand side? It's going to be M3G minus M3A. And do you mind? I'm going to put T2 over here by itself. What was M3? 8 times G, 9.8, minus what was M3? 8 times, and I'm going to go 2.586, and I'll just put a few ones. That should get me pretty close. And I get 57.7. What's your homework? Your homework is the take-home quiz, technically. On Monday, I'm going to finally go over the special relativity test because everyone has finally written. On Monday, we'll mark the take-home quiz, and on Monday, you'll have class time to work on today's homework. But I'll tell you what today's homework, the homework from this. So aim for the take-home quiz over the weekend if you can, please. And you got flex on Monday. But you can try. Oh, I'll let you pick. 1 and 2 are identical. Which one do you want to do, 1 or 2? 1, you say? So circle 1. You can skip 2. 3 has friction. I'll do that one. 4 has 3 masses. Meh. I'm going to pass. 5. Okay. I like 6 better. It's got friction. So far I've skipped 2 and 4. Losing tension there, Julian? I saw that. Put a star next to number 7. The first part, part 8, finding the acceleration of the whole thing is pretty easy. Your hint is just treat that like a 14 kilogram mass, and now it's very similar to question 6. But part B asks, what's the coefficient of friction between the 2 kilogram mass and the 12 kilogram mass? Impress me. That one's tricky. Eight is the 3 kilo. This is the 3 mass one I'll give you. 9 and 10. What are they asking you to find in question number 9 and number 10? I have not done with one like that in the lesson on purpose. It's still going to be winner minus lose, but you know what you get by itself? Not the A. You're going to get the mu by itself. See if you can figure out how to do that. Okay? So I've left that as kind of for you to try and have the aha moment yourself. Put a star next to this. This is actually from a Physics 12 scholarship exam, but I've been sneaking some Physics 12 in with you folks. I will not ask you one this nasty, but see if you can figure it out yourself. There's about 8 minutes left. You can work on the take-home quiz. I will not be doing another lesson on Monday.